Hello, ladies and gentlemen, and welcome to the first Geek Speech broadcast. Now, before I dive into the problem that I'm going to present you today, I just want to tell a couple of words. Why am I doing this? Why am I starting this channel? Well, first of all, to have fun. I really enjoy explaining stuff that I, for example, spent a lot of time to understand. After I understand it really well, I like to just pass the knowledge on. It really makes me feel really well. So I do it for fun, mostly. And secondly, I've noticed that out there are so many channels where they make fun of random and silly things. I don't like celebrities or other stuff I am not so interested in. And I just wanted to, I don't know, provide from time to time an alternative source of relaxation or having fun and just seeing one idea or two which I think they are fundamental, they are interesting, and they are exciting. I just some problems there just really deserve your attention for 1 minute and just think about it for a bit and come up with new ideas from them because they are applicable everywhere. They are not just complicated stuff with integrals, derivatives, and a lot of computations. They are just things that you just need to use your brain a bit, and I mean, you have a spark, and it really trains your creativity. I feel like it. So this is the handshake syndrome problem. This is not the problem that determined me to talk about transformation invariant. We'll have a more complicated problem later. I will get to it right away. But first, I just wanted to get you a feel about this transformation invariant and just start with this very simple problem. This is from Kvant. It was not called handshake syndrome. Of course, it's a mathematics um, publication, monthly or weekly. I do not remember. What is certain is that this problem is from there and it got just stuck in my brain, and it's very good for illustrating what transformation invariant, I mean this fancy term here, really means. So the problem is very simple. You have n people going to a party, and whenever x and y meet for the first time, they make a handshake. So if X and Y know each other from previously, they don't make a handshake. If they meet there, they make a handshake. So, and anyways, there can be any protocol you want. They might know themselves from previously, but they might not meet at the party. I mean, if the party has 100 people, it's not necessarily that I and J or X and Y meet at the party. So anything can happen at the party. We don't know. And you have to prove, I mean, I've written here very nicely, let O be the number of people that experienced an odd number of handshakes. So whenever X and Y meet, the number of handshakes of X goes up with 1, and the number of handshakes of Y goes up with 1. So if O is the number of people that experienced an odd number of handshakes, I mean, you can imagine some of the people made 1 handshake, so that is odd. Some of the people make 8 handshakes, and that is even. Now, if you number all the if you count all the people that experienced an odd number of handshakes, that is even. So no matter what happens at the party, prove that the number of people that experienced an odd number of handshakes is even. And you could say, okay, but there can happen anything there, and you are right, and you have no way, absolutely no way to tackle this if you don't look. I mean, whenever there's a handshake, something changes. The total number of handshakes changes. That would be the first thing that comes to my mind. Um, Something changes in that system. Let's be fancy and call it system. The state of the system changes. Now, let's see here, this is my system, P1, P2, P3, P4. You can call this as the states of the system. They count how many handshakes did guest 1 do, did guest 2, guest 3, and guest 4. Initially, they are all 0. Let's say a handshake happened between P1 and P3. Automatically, the number of handshakes of P1 goes to 1, the number of handshakes of P3 goes to 1, and you have a new state of the system. So you can say that this is a transformation going from this state to this state, and we need to find an invariant, something that doesn't change. Since we are talking in even and odd, I mean, the most logical thing is to look at t, the total number of handshakes, and see that it remains even. Here it is 0, here it is 2, and whenever a handshake happens, the total number of handshakes changes with 2, but its parity doesn't change, it remains even. Okay, now let's take all the people, I mean, the number of handshakes that each guest at a party did. Now let's add them together. I don't know what's here. Let's say that here it's is for example even. Let's say that here it's even. Let's say that here it's odd, and let's say that here it's odd. Now, whenever I add even guys, so to say them, the parity, the total number of handshakes doesn't change. So the parity of t doesn't change. So even guys, they can go home. I'm not interested in them. Let's look at the odd guys. So if you add an odd guy, the parity of t changes from even to odd. If you add another odd guy, it changes from odd to even, and so on and so forth. Now imagine these guys would be in an odd number. If it would be in an odd number, you have odd plus odd, odd plus odd, odd plus odd, and one guy with odd. So the t will be odd. But we have already proven that t is even. So by looking at the total number of handshakes and acknowledging that t has to be even, because this is how a handshake works, both number of handshakes and x of x goes up, and both number of handshakes of y goes up. So t is even. This doesn't change. So you need absolutely to have the number of people that made an odd number of handshakes, they need to be in an even number. So that was easy. Just wanted to tell you that if you want to pause me while I'm presenting the problem, given and prove, I mean, go ahead, pause me, try to tackle the problem yourself, and then you can just come back to it. If not, just enjoy the explanation. So the next problem is the name game. Now, the name game is more elaborate, and as you can see, I haven't written anything because I just want to explain it to you live. So the name game is quite simple in formulation, but not that easy to figure out. So you have how do you call a pile of coins, let's say. So you have pile 1. You don't stop, but you can have as many piles as you want. Pile of coins, p3, p4, p5, p6, p7, whatever. And in each pile you have a number of coins. Let's say you have 10, you have 11, you have 19, 18, 17, 16, 17. Good. Now, you have player 1. I did a great job in just numbering the piles P1. So I will just call player 1 X and player 2 Y. So X just grabs as many coins as he wants from one pile. So X looks at a pile, says, ha, this is my pile, and just grabs. He can grab 1, he can grab 19 from this pile. I mean, he has to grab at least 1 from one pile, and only from one pile. And then guess what Y is going to do? Y is going to choose another pile and just grab from 1 until, let's say from this pile until 17. Of course, he can choose P3, and if there are, for example, 12 coins remaining in that pile, he can just take all the 12 coins. So these are the rules of the name game. And the problem here is who wins the game? What is the optimal strategy to win the game? We can simplify it and say, okay, the requirement, we can simplify it. I mean, the way it is formulated, we can say this is the initial, these are the initial piles. Who wins? Does X win if both players play optimally, of course, or does Y win? Well, I don't know. Let's look at an easier case. Let's say we only have here P1 and P2. That looks easy. And let's say that X is on the move. Now, let's say that X is very, I don't know, greedy and just takes the whole P1 pile. So Y is left with only one pile. He can take the whole pile and he wins. I forgot to say the player that takes the last coin wins. So he was the last who took all coins. He won. Good. So X didn't have a good strategy. Now this is the initial state of the system. What is the final state of the system? So the final state of the system is P2, P2, 0, 0. So after these players take coins, they need to get from this state to this state. I mean, let's say X wants to win and he wants to put Y in this situation, because if he has put Y in this situation, then Y, I mean X means that he was the last one to take a coin. Y doesn't have any coin to take. X wins. So X needs to put Y in this situation. So he needs to make a transformation here that will ensure him the win. Now, if you look here, you see 0, 0. You see here 10, 11. So you might say, okay, if I can keep, I mean, if I can keep the number of coins in P1 equal to the number of coins in P2, then I am absolutely going to win. So let's say here first we have 10, 11. I'm just going to quit writing P1, P2. And Y moves, and Y is going to make here, let's say 10, 10. X moves, I'm sorry. Then Y, let's say he's going to take 9 from one pile. So we will be left with 1, 10. And then X says, hey, my job is simple. I just need to keep the number of coins in one pile equal to the number of coins in the other pile. And he says 1, 1. And now Y, he has no other choice than to take one coin from one pile. So 0, 1. And then X takes the other coin, 0, 0, and Y loses because Y doesn't have any coin to take. Good. So it's simple for 2 piles. However, what happens for 3 piles? Because things get much more complicated. We can try a case. Let's take a very simple case, P1, P2, P3, and let's say here it's going to be 1, here it's going to be 2, and here it's going to be